Thank you very much, and good morning, everybody. My name is Angel Muñiz from the European Marine Board Secretariat, and I'm here to represent the remediation project, which is actually a sister project of the URban. So it was really interesting to see how they solve many of the challenges that also somehow these remediation also face. So that was also really interesting. I have the honor, but also the responsibility to try to summarize the remediation project in 10 minutes because this project will finish in 1 month. But basically, remediations is to reduce chemical pollution through innovative nature-based water treatments. Kind of like a narrative, and I'm taking advantage of the footer of the presentation template. So this is a mission project. So the EU missions to restore our ocean and waters is an initiative of the European Commission to advance technology development, innovation to actually solve solutions the society faces, like for instance the degradation of our marine environment. One of the objectives of this mission is to prevent and eliminate pollution of our seas, oceans and waters. And then to implement the mission, we have what we call the mission lighthouses. So in each sea basin and also in the Danube River, there is a target objective. And for instance, in the Mediterranean is to prevent and eliminate pollution. As you might know, in the Mediterranean, humanity has been living there for millennia. So we live there, we grow crops there, we fish there, we also use it for transportation. And then in more recent times, we also do heavy industry. We might have like a more industrial developments. And also that means that it's actually being polluted. So that's one of the things that remediation is a Mediterranean lighthouse project, and also to aim to distress the Mediterranean from pollution. Just as a little explanation about wastewater treatments. So of course, when you have water for instance, from a city, you have to filter the water when it comes into the water treatment plant. Then you have the primary treatment, where it's by basically sinks the particle matter that is in the water. Then you have a secondary when you have like a microbial breakthrough of organic matter, and then you can have tertiary, which is also treating nutrients, and then you can have also a quaternary if you want to target more specific pollutants like pharmaceuticals or another industrial waste. And then also you have disinfection to remove potential harmful organisms. Just as a reference, this is for environmental protection regulations. This is a black box. So in general principle, the pollutants that have to go in has to be bigger than what comes out. So in principle, whatever goes in and whatever goes out has to be cleaner. So in general, regulations doesn't care what kind of technology is used, what kind of processes, has to be cleaner afterwards. So that's also the added value of the remediation system, that also can be plugged after any of the already existing treatments. So you can see here a picture of the system when you have some containers and also the photobioreactors. And the added value of this system is that it's microalgae-based. So it's basically the microalgae present in the water will do the dirty work, let's say, to clean the water. On how does it work? And also I will come back to that we call it the remediation approach. So you have the water that you want to treat. It could be natural waters, but also it could be from wastewater. Then it goes to the system. As I said, with the container and the photobioreactors, and then within this container, you have at the back, you have the dirty water that also been, with a different probes and different measurements, because of course you need to assess what kind of pollutants are in this water, and you know what needs to be treated. So you need to measure this. Then that water that has been measured, it goes through the different photobioreactors. So basically, these photobioreactors, they promote the growth of the algae that is naturally present in the water. So you don't have to add any other species, you don't have to add any chemicals and so on. It grows naturally. So if you are a particle of water, you will travel through these different photobioreactors until you reach the end, and of course you can determine how long will the water stay in this system or not. So that's also quite flexible, depending if you have a really dirty water or many nutrients to pollute and so on. So of course the microalgae will use the nutrients that is present in the water, and then also they will capture different pollutants that is present in the water. And it's also these photobioreactors. They act as a kind of like an ecosystem in its own, because then when the algae die off, it will get remineralized by the other algae, use a nutrient, so it's you don't have to clean it up too much. Then this water goes to this other tank that you can see at the forefront. You can see that the water is a little bit clearer, and it's also something that I learned, because I'm not really expert on wastewater treatment, is that of course you also have the color of the water. So if you see that is the color is brown, it means that, you know, it doesn't mean that the water is dirty, it's just that the color of the water. So then, of course, they measure it again to see how the pollutants has been reduced and so on. And then, of course, we tested this technology, and then it wasn't released to the environment, but we also have a system where you can monitor, and you can see one of the buoys here in one of the test cases, where it was monitored that the pollutants in the environment and so on. So this is just a summary infographic of what I just explained, and it's also I will present in a bit the different test sites. But then I want to highlight here is that the information coming from the sea trials. So basically, all these buoys that are in the environment at the end of the rivers, or also in marine waters. That information is transmitted to the European Maritime Observing and Data Network, so EMODNet, which also could be, contributing to the digital twin of the ocean. The testing sites, and it's also I will see, and I will put different images of how the evolution of the water. So one is in Taranto in Italy, where it was also the natural water. So this is when they just installed and you have like clear water. Then we also tested in a wastewater treatment plant in Attica in Greece, and then also in wastewater treatment in Kocaeli in Turkey. We helped local authorities in Bulgaria, Egypt, Moldova, and Morocco to have replication strategies and roadmaps to potentially implement this kind of systems. So, of course, we didn't fund the implementation of this technology, but just to check, what kind of water, what kind of objectives do they want to clean the water and so on. So this is also in terms of for other projects, this is what we did, where association a call for associated regions. Also, what I mentioned is we call it the remediation approach, because of course, not only the technology and the system, but also there was an important component is stakeholder engagement. So we did at the beginning in the different test sites, and also we will do in the next month other stakeholder workshops, and also we engage with the local communities and local policymakers, and also they had visits from schools and so on. So in general, people see it as a positive social impact, because as the microalgae is doing the dirty work, you don't have to ask for exotic chemicals and so on. So it could be also locally produced, the things that you need. So it also could be a turn and a positive turnover to the local communities. Just to present the results and recommendations, and I'm happy to announce that the A policy brief explaining all this is now officially launched, so you can scan the QR code, and in a bit I will put in the chat the link to download it. So as a result, the remediation system is scalable, adaptable, and also can accommodate local and seasonal variations. You can have also more information in the policy brief on what kind of authorities are targeted for this kind of technologies. We proved that has been removal of nutrients, metals, industrial chemicals such as PFAS, pesticides, and pharmaceuticals from wastewater and natural waters. And also there is a reduction of operational expenditure. As I said, the microalgae do the dirty work, and also has much lower carbon footprint and facilitated treatment of urban industrial wastewater for reuse, because also in the Mediterranean, every drop of water is important. So it's also really important that the reuse of this water, of the treated water, is promoted. In terms of recommendations, of course, the most important one, that is pollution prevention must be a priority, because we will be never able to treat 100% of the pollution. So it's cheaper to treat the pollution that is not there. So it's better to to prevent pollution entering in the Mediterranean or other environments. Of course, we also promote or call for establishing clear and specific removal targets and standards for these emission levels of emerging pollutants, because as you might not know, but then for PFAS, there are currently like 10,000 different sorts of PFAS, so we have to know which one do we want to target, because to measure, because it's impossible to measure all and then also to treat all. Also for the biomass that's potentially coming from these wastewater treatments. We also call to develop a standardized monitoring and a clear technical guidelines, because sometimes it depends on how much the water, if it's going to be used for drinking, if it's going to be for reuse, if it's going to be used for agricultural purposes and so on. You have different ways of measuring and so on. So there should be a standardized monitoring and guidance on that. And also in the revised Wastewater Treatment Directive that is currently in place now at the EU, this wastewater treatment needs to reduce the CO2 emissions. So there is also should be some standards on how we're going to do that and so on. Of course, we call to recognize microalgae-based wastewater treatments, because this is not really currently used in wastewater. So this is a nature-based solution. And then also we call for to incentivize to promote the deployment of real-time monitoring and early warning systems, because if you have this kind of buoys in natural environments, you can also detect accidental leakage from industry and so on, so that could also provide early warning and not have to wait to the environmental impacts. And then lastly, we call to incentivize the public-private academic partnerships in diverse sectors, because for instance, these kind of technologies could be used for wastewater treatment, so to treat wastewater from hospitals, for instance, because you will have a lot of pharmaceuticals reaching the environment, so it could be used for that. And then, of course, the kind of collaborations between public and private organizations can also explore alternative uses of the resultant water, and also biomass, which also could be used for energy generation. Finally, I would like to give all the full credit to the team, to the consortium, and this is a group picture we take in front of the one of the test sites. So of course, I'm just presenting. I'm just a messenger of this project, but I'm happy to be part of this project. It has been really interesting. I hope you enjoy the policy brief. You can always ask me some questions, so I will leave it like that. So thank you very much for giving me the opportunity to present the remediation project.